Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says. So imagine we're talking about something so incredibly tiny, a fragment of an asteroid, smaller than a grain of sand. And yet, within this microscopic speck, researchers have just found what amounts to a 4.5 billion-year-old time capsule, pristine and untouched by Earth.
And the resolution they achieved is what truly blows me away. We're talking about mapping the chemical composition of this asteroid dust at a staggering 20 nanometer scale. To give you a sense of that, a human hair is about 80,000 to 100,000 nanometers thick. They're looking at something 4,000 times smaller than that.
Wait, so they're not just saying, oh, this asteroid has X, Y, and Z chemicals in it. They're saying, we found X here, right next to Y there, and Z is tucked away in this other specific spot, all within a microscopic sample?
Exactly. They're seeing the precise architecture, the arrangement of these ancient molecules, which tells us a completely different story than if they were just looking at a blended average. It's like discovering the individual brushstrokes in an ancient painting rather than just knowing what the finished masterpiece looks like.
That's wild. And this isn't just any old space rock, is it? This is from asteroid Bennu, brought back by NASA's OSIRIS-REx mission. Which brings us to a fundamental question. Why did NASA spend over $1 billion to collect a cup full of dirt from space when we have meteorites literally falling to Earth for free all the time?
It's an excellent question, and it gets right to the heart of what makes these samples so revolutionary. The core issue with meteorites, as fascinating as they are, is contamination and alteration. Think about what happens when a meteorite enters Earth's atmosphere. It's screaming through at incredible speeds, flash frying its exterior, creating what's called a fusion crust. That thermal alteration can destroy or significantly change any delicate organic molecules inside.
So heat is one problem. I imagine the impact itself isn't exactly gentle on the chemistry either.
Precisely. But even if it survives the atmospheric entry relatively intact, the moment a meteorite hits the ground, it's exposed to Earth's biosphere. Our planet is a living, breathing, watery place. Meteorites act like sponges. They soak up terrestrial water, oxygen, and within hours, they're colonized by Earth bacteria. If you find complex organics like amino acids in a meteorite, you then have to go through an incredibly rigorous process to prove they're truly extraterrestrial and not just terrestrial hitchhikers. It's a chemical deduction game with very high stakes.
So a meteorite is essentially compromised from the get-go. It's been baked, battered, and then effectively marinated in Earth's primordial soup.
A perfect analogy. And that's where OSIRIS-REx and the pristine Bennu samples come in. The team, including researchers from Stony Brook University and Lawrence Berkeley National Laboratory, bypassed this entire problem. From the moment that sample was scooped off Bennu's surface, through its journey home and right up to its analysis, it was kept in a highly controlled inert environment. We're talking ultra-pure nitrogen gas, never exposed to Earth's air.
So they were essentially doing surgery in a pristine clean room the entire time.
More like handling a precious artifact that would degrade instantly if exposed to the elements. And this strict isolation is absolutely critical. Because they maintained it, the researchers can say with 100% certainty that the carbon, hydrogen, nitrogen, and oxygen bonds they observed are truly 4.5 billion years old, utterly untouched by earthly influence. That's the pristine advantage. It's a direct window into the early solar system.
Which brings us to the methodology, because if you have this incredibly precious, pristine sample, you can't just, as you said earlier, grind it up or dissolve it. You need techniques that are, well, non-destructive, right? And that's where the nanoscale comes in.
Exactly. Imagine you have a single, precious page from an ancient manuscript. You don't want to burn it to see what it's made of. You want to read it, analyze it, understand its composition without damaging it. The researchers used two incredibly advanced techniques. The first was nano-FTIR, or nano-Fourier transform infrared spectroscopy.
That's a mouthful. What does it actually do?
So, traditional infrared spectroscopy is like shining a specific kind of light on a sample and seeing what wavelengths it absorbs. Different molecules absorb different wavelengths, creating a unique chemical fingerprint based on how their bonds vibrate. But traditional IR microscopes have a resolution limit.
Nano-FTIR overcomes this by using an atomic force microscope, essentially an incredibly tiny metallic tip that hovers just above the sample. This tip acts like a miniature antenna, scattering the infrared light and allowing them to measure the chemical fingerprint directly beneath it.
So it's like a hypersensitive, microscopic probe that can feel the molecules and read their chemical signature without touching them too hard or destroying them.
Precisely. It allows for chemical mapping at an unprecedented resolution. They paired that with Raman spectroscopy, which uses a laser to look at different vibrational modes. While IR is great for identifying functional groups, Raman is excellent for understanding the structure of carbonaceous matter, and the Raman data here was crucial. It showed the carbon in Bennu is highly disordered and thermally minimally metamorphosed.
Meaning it hasn't been baked by extreme heat, which is a good sign for fragile organics.
Exactly. It's another piece of evidence that this material is truly pristine. Now, let's revisit that 20 nanometer resolution. We talked about a human hair. Let's try another analogy. Think about a single strand of human DNA, which is about 2.5 nanometers wide. A typical virus is between 20 and 300 nanometers.
So they're basically looking at the equivalent of a virus-sized piece of an asteroid, mapping its chemical makeup molecule by molecule. That's just mind-boggling.
It is. This isn't just about identifying what chemicals are present in the asteroid overall. It's about seeing exactly where those chemicals are located in relation to one another. This spatial mapping reveals the architecture of the asteroid's chemistry. It's the difference between knowing the ingredients of a cake and seeing how those ingredients are distributed, where the chocolate chips are, where the flour is, where the sugar crystals are clumped.
And that level of detail, that nanoscale mapping, led them to debunk a long-held assumption about how water interacted with these early asteroids, didn't it? The idea of the uniform soup.
Yes, absolutely. Before missions like OSIRIS-REx and Hayabusa 2, a prevailing assumption was that when ancient carbonaceous asteroids experienced aqueous alteration, meaning liquid water interacting with the rock, it was a relatively uniform process. The internal heat from radioactive decay would melt internal ice, and the water would permeate the rock, creating a somewhat blended, uniform chemical soup.
Like a sponge soaking in a bucket of water. Everything gets uniformly wet and mixed up.
That's a great way to put it. But this 20 nanometer mapping of sample ORX80066 completely shatters that idea. What they found was that Bennu's minerals and organics are distinctly segregated at the nanoscale. It's not a soup at all. They identified 3 highly specific recurring chemical domains.
What were these distinct chemical neighborhoods?
First, they had allipothic-rich regions, which are areas dominated by open-chain organic compounds. Then, carbonate-rich regions, where you find minerals like calcite and dolomite, which are known to precipitate out of liquid water. And most interestingly for astrobiology, nitrogen-bearing organic-rich regions, areas dense with complex organics that contain nitrogen.
And the key is that these weren't all mixed together.
Exactly. Their statistical analysis of these 20 nanometer maps showed strong negative correlations between the allipothic signatures and the other 2 domains, and very little correlation between the carbonates and the nitrogen-bearing organics. In plain language, these chemicals just don't like to mix. They sit in their own isolated pockets. The researchers even found that organosulfur compounds were strictly restricted to the carbonate-rich regions, indicating late-stage interactions with salty water.
So instead of a sponge soaking in a uniform bucket, it was more like water flowing through a very intricate microscopic plumbing system, creating distinct microenvironments.
That's precisely the conclusion. Water did not alter Bennu uniformly. Instead, fluids flowed through restricted, highly localized pathways. Think microscopic veins and capillaries within the rock. This created a patchwork chemical environment where different alteration processes were happening mere nanometers away from each other without ever interacting.
That's fascinating. And I know the paper even compared this to asteroid Ryugu, which was sampled by Japan's Hayabusa 2 mission, and found some interesting differences there, right?
A fantastic point for comparative planetology. On Ryugu, previous research found a positive correlation between nitrogen organics and carbonates. They were found together, suggesting that carbonate precipitation happened in regions that retained dissolved nitrogen organics.
So on Ryugu, they did mix.
To some extent, yes, but on Bennu, there was no such association. The fluid pathways were spatially segregated. This tells us that even among primitive, carbon-rich asteroids, the internal plumbing and chemical evolutionary histories were incredibly diverse. Bennu and Ryugu, while both carbonaceous asteroids, clearly had very different internal processes when it came to water.
It also highlights the distinction we always try to make on this show, what we know versus what we're still modeling. We have the hard evidence of the spatial distribution now, the visual proof of this segregation. But the exact timeline, temperature, and duration of that water flow from 4.5 billion years ago, that's still being reverse engineered, isn't it?
Absolutely. The direct observation is the segregation. The interpretation of how that happened, the full hydrological history, is still a complex modeling effort, trying to reconstruct the fluid dynamics of a parent body based on a few grams of rubble. It's a testament to the power of these samples that we can even begin to ask those questions.
And among those distinct chemical domains you mentioned, the one that really seems to have captured the most attention is the nitrogen-bearing organics. Why are those so special?
Well, to understand why this is such a celebrated finding, you need to understand their chemistry. Nitrogen-bearing organic molecules are often described as chemically labile.
Labile meaning fragile, easily broken down?
Precisely. They're prone to change. When exposed to environmental stress, like prolonged heat or harsh aqueous alteration, that water-based interaction we just discussed, these molecules tend to degrade, break apart, or transform into simpler, less interesting compounds. They're the delicate butterflies of the chemical world.
And yet, they found them perfectly preserved inside Bennu.
That's the massive revelation. It means that despite the asteroid's parent body experiencing significant water flow, the restricted, patchwork nature of that flow, this intricate plumbing system, provided safe havens. The water altered the rock, but it didn't wash away or destroy these fragile chemicals.
So the asteroid acted like a series of tiny, perfectly sealed safe deposit boxes for these delicate molecules.
Exactly. And the paper notes a staggering statistic. Compared to the Ryugu samples, Bennu contains approximately 75 times higher ammonia concentration and roughly twice the abundance of isotopically anomalous organic matter. Ammonia is a critical source of nitrogen. The researchers hypothesize that Bennu's parent body may have formed further out in the protoplanetary disk, beyond the snow line, where volatile compounds like ammonia freeze, or simply had a different evolutionary history that allowed it to retain its volatiles better than Ryugu. It really underscores the diversity even among these primitive bodies.
This is the point where I have to step in and put on my journalistic grounding hat, because whenever the public hears water and complex organics found on an asteroid, the immediate leap is to alien life. And we have to be really clear here, right? Finding organics does not mean finding biology.
Absolutely critical distinction, and it's one the researchers themselves are very careful to make. Organics are simply molecules containing carbon-hydrogen bonds. The universe is incredibly good at making organic molecules abiotically, meaning without any life involved. What Dr. Mehmet Yasiltas and his team found are the building blocks of life, not life itself.
So these nitrogen-bearing organics, they're the raw materials, the Legos, if you will, for things like amino acids, which make proteins, and nucleobases, the letters of our genetic code.
Exactly. The discovery proves that the raw, abiotic Legos required for prebiotic chemistry can be synthesized and, more importantly, preserved in the harsh environment of early space. This isn't about little green men. It's about the fundamental ingredients for the origin of life here on Earth and potentially elsewhere.
Which brings us to the grand narrative, the big picture. How does a 20-nanometer speck of asteroid dust impact our understanding of the existence of life on Earth?
It connects directly to one of the greatest open questions in astrobiology: how early Earth, which was a molten, violently bombarded hellscape in its infancy, acquired the water and complex organic chemistry necessary to spark life. The heat of Earth's formation likely destroyed any indigenous fragile organics.
So, enter the asteroid taxi theory.
Precisely. The hypothesis of pseudopanspermia, or the asteroid taxi theory, suggests that during the late heavy bombardment, roughly 4 to 3.8 billion years ago, carbonaceous asteroids like Bennu acted as delivery vehicles. They rained down on Earth, depositing their payloads of water and prebiotic organics onto the cooling crust.
And for that theory to hold water, pun intended, two things have to be true. Asteroids have to be capable of making these molecules, and they have to be capable of protecting them through billions of years in space, and through their own internal geological processes.
And this PNAS paper provides concrete empirical proof for that second requirement. It proves that asteroids can indeed act as safe deposit boxes for these fragile, life-essential molecules. As Dr. Mehmet Yesiltas himself stated, this research demonstrates survival of chemically labile nitrogen-bearing organics through aqueous alteration on a small solar system body, has direct implications for long-standing questions about how organic complexity is built up and preserved in primitive planetary materials. By extension, it may reveal how organics relevant to prebiotic chemistry may have been delivered to early Earth via carbonaceous asteroids and may have played a role in the chemical processes that might have eventually led to life.
That's a powerful statement, and it really brings home the significance of this painstaking nanoscale work. It's connecting the microscopic to the macroscopic story of life itself.
Absolutely. And remember, the OSIRIS-REx mission returned 121.6 grams of material. This study analyzed just a microscopic fraction of a single fragment. NASA has reserved roughly 70% of the Bennu sample, keeping it sealed for future generations of scientists.
Which is a brilliant long-term strategy. They're saving the majority for analytical technologies that haven't even been invented yet.
Exactly. This paper sets a new benchmark. It proves that to unlock the secrets of the solar system, we don't just need to look at the stars with massive telescopes. We need to look at pristine dust through a 20-nanometer lens. And it sets a very high standard for future sample return missions, like the Mars sample return mission, emphasizing just how paramount avoiding terrestrial contamination is to doing world-class planetary science.
So if we boil this down to the most important takeaways, it's really about the value of that journey, that pristine sample, right?
Absolutely. That expensive journey was worth every penny because meteorites are compromised. Sample return missions provide the only truly reliable, uncontaminated window into 4.5 billion-year-old chemistry.
And the scale of the analysis. That 20-nanometer resolution wasn't just a technical flex, it was essential to seeing Bennu's true chemical complexity.
Yes, the power of nano-FTIR allowed them to discover that Bennu's chemistry is highly segregated, a true patchwork asteroid, not a uniform soup.
And that patchwork structure was key to the survival of those delicate, fragile nitrogen-bearing organics, which are the fundamental building blocks of life.
Precisely. It proves asteroids can act as safe deposit boxes for these critical molecules.
Which in turn directly bolsters the theory that these asteroids were the delivery trucks, bringing the necessary prebiotic chemistry to jumpstart life on early Earth.
It's a scientific mic drop for the asteroid taxi theory.
Incredible. So as we wrap up, what big questions should our listeners be pondering after hearing this?
I think two things. First, given the chemical diversity we're now seeing between asteroids like Bennu and Ryugu, what other chemical patchwork architectures might exist out there on other primitive bodies? And second, how does this understanding of pristine chemical preservation in asteroids refine our search for life's origins, not just on Earth, but potentially on other planets or moons?
That wraps up this episode of Paper Trail. Join us next time as we dig into more research worth talking about. If you liked what you heard, share it with a friend or drop us a review.
Keep reading the fine print.